This is the end of week 7. Okay. Anyway, let's go ahead and get started. So welcome back, everyone. What did we do last time? Well, we started talking about general wavelet systems and the conditions, systems and conditions on the coefficients of the wavelets, right? Of the wavelets. And of the dilation equation. So today we're going to keep on doing that. So today we're going to continue proving necessary and sufficient conditions. And sufficient conditions on those coefficients. Let's see, so I finished, let's just briefly review what we did last time. So last time we stopped by showing that the orthogonality of phi of x and psi of x minus k guaranteed some conditions on these coefficients ci, right? So the shifted product of the ci coefficients with our bi coefficients, that is for the Miller wavelet versus the scale function, well, those have to have this condition where the product of the scaled products have to sum up to 0. So this is similar in some ways to the conditions on just the scale function itself being orthogonal to shifted copies of itself, except in that case, instead of it being always equal to 0, it was equal to 0 unless, well, they aligned with each other. But in this case, even if they are aligned, well, you want them to still be orthogonal because they are different, the scale function versus the wavelet. And today we're going to show that it's actually much stronger than that even. We're going to show that the conditions on the BIs are actually extremely strong, and you basically have no choice in the BIs once you've chosen your scale function. And let's see, where did I end? I ended with 11.5, so let's continue with 11.6. So, oh no, we're going back to 11.4 because I did these in the opposite order. That's what was confusing me. So I prefer this order to the order the book gives, but it means that the ordering is slightly out of place. Okay, so that was, well, we showed that the scale function being orthogonal to the wavelet imposed certain conditions. Well, now let's show that the scale function being orthogonal to shifted copies of itself also imposes certain conditions. And this proof, I'm not going to prove it, I'm just going to state it because the proof is exactly the same as in 11.2. But so if we let psi of x be equal to some sum from k equals 0 to d minus 1, bk of our scale function phi of 2x minus k, then if psi of x and psi of x minus k are orthogonal for k not equal to 0, and psi of k is normalized, so that we have the expression, the inner product of psi of x with psi of x minus k dx, that's just going to be equal to delta of k. Well, then what might you guess about the scaled product? Shifted product, sorry, of all the coefficients. Oh, I started writing it out already. But anyway, so as you'd expect, what you basically get is twice the delta function. And this is exactly the same as it was for the scale function, right? So it was orthogonal to all the shifted versions of itself. That's the condition we wanted. And so all the scaled coefficients, except when k is equal to 0, are equal to 0. And the case when k is actually equal to 0, well, then you get 2. And this is exactly the same as in the case of the scale functions. And I won't walk through the proof because it is exactly analogous to Lemma 11.2. Okay, and proved exactly the same way. You do your integral thing, you spread out the summations, you move the summation to the front, and then you're done. Okay, now we're going to spend most of the day on a much more complicated proof. So we're just going to put the much stronger constraint on the BKs. So if we have that, I'm going to use this notation just because we're going to be doing a number of inner products. The inner product of phi of x and phi of x minus k is equal to delta of k. And we have that phi of k x and psi of x minus k is equal to 0 for all k, then bk is equal to -1 to the k times c sub d minus 1 minus k. Okay, so basically what we're saying is that the coefficients for the bk's are actually exactly the same as the coefficients for the ck, except you do alternating plus or minus. So for the sake of completeness, I think like this is actually also fine, but if you just make all of the bk's negative of what they were originally. So that's also fine, but we're just going to assume without less generality that they're the same solution. And this is a rather complicated proof. And it will involve, hopefully you guys remember your Fourier, Fourier transforms, because the proof of this will involve that. So the first thing we're going to do is, well, if we're going to think about discrete Fourier transforms, we need to have some function, right, that we're doing a Fourier transform on. So let's think of bk and ck as discrete functions. Functions b from z to r and c from z to r, given by bk is equal to bk and ck is equal to ck. So a pretty standard setup. You're just thinking about these vectors as finite support discrete functions on the set of integers. And of course, these have support just 0, 1, 2, 3, 4 through d minus 1, which is, of course, a subset of the integers. And so now let's recall the discrete convolution. So if you have two functions, f convolution g, that's evaluated at some point k, that's just going to be equal to the sum for m equal to minus infinity to infinity of f of m g of k minus m. Okay, so just the normal convolution operator. You take one vector, you take the other vector, you flip the second vector, and then you multiply them together after the appropriate shift. And obviously the value of this function outside of your range, so the support domain, so if k is equal to minus 1,000, obviously that's going to be outside of the support, and so you're just going to get 0. And so you're going to do the same thing that we're doing earlier of these like shifted products, except you're flipping the one of your vectors. Okay, so given that, we can now we're now going to make use of the fact that excuse me, these products here, where we were talking about these things, these look sort of like convolutions, right? And basically, we're going to rethink about them as convolutions, and then we can take everything into the Fourier domain, into the frequency domain using a Fourier transform, and then reason with them there, and then come back. So let's first recall a couple things. So first, oh, wrong color. By lemma 11.5, we know that the sum from j equals 0 to d minus 1 of cj bj minus 2k is equal to 0 for all k. Okay, let's just recapitulating the statements. Oh, sorry, let me bring up chat in case anyone's asking any questions. Okay, no one's asking anything in chat. So now this isn't quite a convolution, right? Because you're jumping by steps of 2. What can you do instead? Yeah, just reparameterize it as, and the way we're going to do this is actually going to be a tiny bit weird, but it's not, it's pretty straightforward. So this also implies that the sum from j equals 0 to d over 2, sorry, let me write that a little bit more clearly. D over 2 minus 1 of c2j b2j minus 2k plus the sum over j equals 0 to d over 2 minus 1 c sub 2j plus 1 and b sub 2j plus 1 minus 2k is equal to 0 for all k. So we're splitting the terms of the summation up into even and odd terms. And now what we're going to do is we're going to do exactly that. Let's let the vector, let's say c sub e, be equal to C naught, C2, C4, all the way through C sub D minus 2. And let's let CO, so that's an O, not a 0. Doesn't really matter, so I'm not going to be using C as a 0 anywhere. I mean, not capital C0 anywhere. Let's make sure that's capitalized. This is going to be the vector of odd terms, C1, C3, C5, all the way to C sub D minus 1. And we're going to do the same thing for BE and BO. So this is going to be the vector of coefficients B0, B2, through BD minus 2. This is going to be B1, B3, through B sub D minus 1. Okay, and we're also going to define CE reversed as, well, you're going to reverse the vector, C sub D minus 2, all the way through C2, C0, and so on. So that's reversed. Well, now that we've redefined our vectors in this way, you can rewrite this statement here as a sum of convolutions. So when we know that C even, take the convolution of that with B even reversed, and we have to reverse it because, well, convolution's reversed, so we're effectively, you can think of this as a cross correlation. That is actually what this is. But we're going to use this convolution notation, evaluated at K plus C odd convolution with B odd reversed at K. It's going to be equal to 0 for all K. So you can also think of these as, if you think of these as functions, basically the sum of these functions is identically 0. Okay, and we can do this the same thing. So we did this for lemma 11.5, but we can also do this for all the other lemmas. So by lemmas 11.2 and 11.4, we have that the sum over our Cj, j equals 0 to d minus 1 of Cj minus 2k. That's equal to 2 delta of k. And the sum from j equals 0 to d minus 1 of bj minus 2k. That's also equal to 2 delta of k. And then that implies that, well, we break these up in the same way. So j equals 0 to d over 2 minus 1 of our C2j minus 2k, plus sum from j equals 0 to d over 2 minus 1 of C2j plus 1 and C2j plus 1 minus 2k is equal to 2 delta of k for all k. And this here, that's, of course, you can rewrite this in the same exact way. So this implies that C even convolution with C even reversed of k is plus, and you can drop the of k since these are, we're thinking about these as functions right now, plus C odd convolution with C odd reversed of k is equal to 2 delta of k. And you really see now that we're really using the delta function as a function. So now we're treating all these other vectors as, well, functions in the same way that the Kronecker delta function is a function on the discrete space of integers. And also, I'm not going to rewrite out the summations because it's the same picture now, but also you get from the other one that BE convolution with BE reversed of k plus B odd convolution, not convolution with B odd reversed of k is also equal to 2 of delta of k. Okay, everyone happy so far? So then all we need to do is we can rewrite this system of equations. So we have 3 equations here, this one, and this one. We can rewrite these in a matrix form. So we're going to rewrite these as matrix. And it's going to be CE, CE, C odd, B even, B odd, convolution with C even reversed, B even reversed, C odd reversed, and B odd reversed of k, but I'm going to drop that. is equal to the matrix 2 delta of k, 0, 0, 2 delta of k. Yep.
Do you do that like Hadamard wise? Like entry by entry wise, or like?
No. So we're doing this. So basically, if you take the first row and the first column here. So that's the notation we're using. Like occasionally you might see some different notations, but basically we're taking lists with lists.
Yep. Okay.
And you notice that that's precisely list statement here.
Okay.
Yeah. Okay, so now that we have lists, we have some convolution operator on these discrete functions. And so we're going to take a Fourier transform. And Fourier transforms are magic, but you should review them if you are not familiar with them. I'm not going to go into too much detail. If enough people say you haven't heard of Fourier transforms, maybe I'll do that tomorrow, but hopefully you guys have seen Fourier transforms before. If not, send me an email. Wait, you haven't, or? Oh, okay. Well, let me add that to the stuff that I'm going to cover tomorrow, because it is important that you guys see Fourier transforms. Like that is actually more important than wavelets. I just sort of assumed that you guys had seen them. But okay, so I will do that tomorrow, since I don't have a lecture for that prepared today. But so we're going to take the discrete Fourier transform. Okay, do I have notes on that prepared? I might from a couple years ago. Let me take a quick look. So I think last time I had the Nyquist sampling theorem that people hadn't done. No, I don't have the discrete Fourier transform explicitly written out. I have like Fourier series in general, but okay, I will do that tomorrow since that is actually quite nice. This is some quite nice results there. So we're going to take the discrete Fourier transform and we're going to call that f. And when you do that, basically in the Fourier, after you do the Fourier transform, the convolution operation just becomes an ordinary multiplication. So you're left with f of CE, f of CO, f of BE, and f of BO times f of CE reversed, f of BE reversed, f of CO reversed, and f of BO reversed. Oh, sorry, put the reversed in there. It turns out to not actually, it doesn't really matter. Applied to some other variable. So obviously you change variables whenever you take the Fourier transform. I'm going to call this k hat. And that's just equal to 2, 0, 0, 2. I'll go over this a little bit more tomorrow, but for now, just accept that when you take the Fourier transform of a Kronecker delta, what you get is just 2. But now we have this really simple matrix equation, and let's just sort of ignore that for now and just think of these as matrices. Well, then you can take the determinant of both sides. We're going to take the determinant of both sides of these matrices in your transform space. So taking the determinant, well, what are you going to get? You're going to get f of CE times f of B naught, of B0, not B naught, minus f of BE times f of C0 times f of CE reversed times f of B minus f of CO reversed times f of BE reversed. Yeah, that's right, is equal to 4. Okay. So now this is in frequency space, and we know that this is all equal to 4. And you'll notice that the left term and the right term look very, very similar, except one is reversed and the other one isn't. So we'll note a few things about this. And so these are properties of Fourier transforms. So f of x reversed in the frequency space is the same as f of x reversed. Okay, so this is just the time reversal property of Fourier transform. So you can move all of the reverses outside into the after you've done the Fourier transform. So after you've done the discrete Fourier transform, you end up with a vector of the same length as you originally started out with. And you can also think about reversing that vector. And so that's what we're doing here. Time reversal of Fourier transform. And it turns out that f of x of k is symmetric about its central bin. Why is that the case? For those of you who have seen Fourier series, when you take the Fourier transform of a, in this case, a real function. Oh, so the answer is that it turns out it's because it's a real function, and when you take the Fourier series of, Fourier series are functions, Fourier transforms like map from complex to complex vectors, right? It turns out that if one of your vectors is entirely real, when you do the Fourier transform, the map that it sends it to is symmetric. And this is a well-known transforms, which I may also do tomorrow since I'm getting some blank stares. But basically, this is symmetric. So it's symmetric about the central bin if X is real. And together, this means that these two things are equal. And so thus, we know that f of CE times f of BO minus f of BE times f of CO squared is equal to 4. And without loss of generality, I'm going to say that the square root of 4 is 2. And it turns out that sometimes you also get -2, but it doesn't matter for the reason I mentioned earlier. If you like carry through the logic, it just ends up meaning that you can take a negative sign of all your coefficients, and you still get an answer that's reasonable. But we're going to ignore that for now. So without loss of generality, we're going to assume that f of CE b of f of B0, not 0. I keep on saying 0. That's an O. It is an O. So B odd minus f of B even times f of C odd is equal to 2. Now, the nice thing about Fourier transforms is that we moved over into the frequency space for, we moved over using the Fourier transform, and we can move back. So now we do the reverse Fourier transform, and this implies that CE convolution with BO minus BE convolution with CO. Actually, let me write this in a slightly different order to make life easier for us later. BO convolution with BE is equal to 2 delta of K. Okay, so now what we did is we turned this sort of ugly system of equations, and now we just have a single equation here that talks about the way these coefficients relate to each other. Now, we're just going to do a couple things. The first thing we're going to do is we're going to take a convolution by CE reversed. And what happens when we take the convolution on both sides by List? What we end up with is CE reversed convolution with CE, convolution with BO, minus CE reversed convolution with CO, convolution with BE is equal to 2 times CE reversed convolution with the delta function, right? So now recall that CE reversed, minus CE reversed convolution with BE is equal to CO reversed convolution with BO. Why is this? Yeah, we had the result earlier, which was what we did just up here. Which one was that? This one here. We showed that they add up to 0, which means that one is equal to the negative of the other. And together, this means that we can combine these. And so you end up getting that this equation turns into CE reversed convolution with CE convolution with BO plus CO reversed convolution with BO convolution with CO, which is equal to 2 CE reversed convolution with the delta function. And we can bring out some of these terms, and you get CE reversed convolution with CE plus CO reversed convolution with CO convolution with BO. So I'm changing the order of my convolutions a little bit. Is equal to 2 CE reversed convolution with the delta function. But when we do that, we know what listing here is, right? What's that? Yeah, so this is another delta function. So 2 delta k convolution with BO is equal to 2 CE reversed convolution with delta k. And so this actually just implies that CE reversed is equal to BO. And what that means is, this means that CI is equal to BD minus 1 minus I for any even I, right? And similarly, I'm not going to walk through all this logic, but you can sort of see what happens. You do the same thing. So similarly, convolution by CO reversed yields something slightly different. You end up with a negative sign instead. Minus BE is equal to CO reversed, which implies that CI is equal to minus B sub D minus 1 minus I for odd I. And together, that means that CI is equal to minus 1 to the I times B sub D minus 1 minus I for all I. So effectively, we have basically no degrees of freedom once you've chosen your CIs. So once you've chosen your scale function, the wavelet that you get out of it is completely determined, or like the wavelet is completely determined by those coefficients. And the only choice you have is whether or not you're going to flip it symmetrically. And if you think back to the Hara wavelet, that sort of makes sense, right? Because if that's your scale function, lat is a wavelet, but so is lat. And they're not really different in some sense. And so we're going to ignore, and in fact, they're really not different because you just multiply one of them by minus 1. So if you're thinking about them as a basis, all you're doing is you're taking the basis elements and multiplying them by minus 1, which doesn't change anything. Okay, so these have all been necessary conditions, right? So these are all conditions that are necessary if you want to have an orthonormal basis of wavelets and scale functions. And we're now going to show that these conditions are basically also sufficient. So sufficiency conditions, C condition for orthogonal wavelets. And this is Lemma 11.7 in your textbook. So if B sub k is equal to minus 1 to Li k of B, C sub D minus 1 minus k, then we know that the inner product of phi of x and psi of 2 to the j x minus L d is equal to 0 for all j and L. Integers, obviously. So basically what we're claiming here is that if we have this, then you also get this orthogonality property that we care about. And let's prove this. So, well, we're going to use the same strategy we've been doing every single time, except so if we have this inner product, we can break it up. So not quite that inner product. We're going to do a simpler one first. So this is where the two are of the same scale. So basically, I'll do a scale function and the scaled versions of the mother wavelet. But we do the same thing. So this is sum from I equals 0 to D minus 1 of CI, phi of 2x minus I, times the sum from, I need to use a different letter, J is equal to 0 to D minus 1, B sub J of phi of 2x minus 2k minus J, dx. Use the usual tricks. This is equal to some double sum over I and J of CI, BJ times the integral from minus infinity to infinity of phi of 2x minus I times phi of 2x minus 2k minus j dx. We rescale, we translate, and you end up getting that this is equal to 1/2 times the sum over I and j of ci bj times, where was I? Times the integral from minus infinity to infinity of phi of y times phi of y plus I minus 2k minus j dy for this changed variable. And notice also that we know what our bj's are. They're just -1 to the I time, or -1 to some power times your some other c. That's equal to 1/2 times the sum over ij of -1 to the j ci c d -1 minus j times some delta function I minus 2k minus j. And of course, now we have a delta function and a double sum. You can reduce it down to just a single sum. So that's equal to 1/2 times the sum for j equals 0 to d minus 1 of -1 to the j c sub 2k plus j and c sub d minus 1 minus j. And now we're going to make use of another fact, which is because d is even, what can you say about the summation? Yeah, exactly. So you get cancellation of all your terms. You can sort of see that. So this is 1/2 c2k cd minus 1 minus c2k plus 1 cd minus 2 and so on. But on the other end, you get cd minus 2 c2k plus 1 minus cd minus 1 c2k. And obviously, these terms all cancel out. And you get 0. Okay, so if you have these coefficients, then you do automatically get that this particular form of orthogonality for the scale function and the translated versions of the mother wavelet. But now we know that, let's see. Now we know that we can obviously substitute this in. So if you rescale both the mother wavelet and the scale function, this still holds, right? So plus we know that phi of 2 to the j x minus m and psi of 2 to the j x minus k dx is equal to 0 for all m and k by substitution. So basically, if you rescale them, nothing changes. They're still orthogonal in the same way. But of course, the whole point of building up these wavelet bases was that at each level, they're composed of some linear combination of the level below them, right? So note that phi of x is a linear combination of phi of 2 to the j x minus m over m. Unless we get that the integral from -∞ to infinity of phi of x times psi of 2 to the j x minus k dx for any the indices is equal to the inner product of, well, you break up the sum over m of phi of 2 to the j x minus m times psi 2 to the j x minus k dx. But each of those inner products, once you move the integral inside, is just 0, because we just showed that at the same scale they're orthogonal. And so therefore, this sum is also equal to 0, which completes this proof. And lastly, we also need to show orthogonality of each of the different level wavelets to each other, right? And so that's our final lemma. I think this is our final lemma. Yeah, this is our final lemma. This is the lemma 11.8. And so if our b sub k is equal to -1 to the k c d minus 1 minus k, then we also know that the integral from -∞ to infinity of 1 over 2 to the j psi of 2 to the j x minus k times 1 over 2 to the l psi 2 to the l x minus m dx is equal to delta of j minus l times delta of k minus m. So what we're saying is that in order for them to, that they are orthogonal, and in order for the inner product to be non-zero, you have to have j is equal to f. You have to have the same wavelet. And you notice here that I have put in the rescaling factor here, the 2 to the j and 2 to the l rescaling factor, basically because if you want a really, really thin wavelet to have inner product with itself being equal to 1, it has to be really tall. And so we need to rescale down to get the orthonormality that we cared about. And this proof here is, again, fairly straightforward. So So the integral from minus infinity to infinity of psi of x minus k dx is equal to some double sum. I'm not going to walk through all of it again, over I and j, bi, bj, times some delta, I minus 2k minus j, which is equal to the sum over I equal 1 to d minus 1 of bi minus 2k. But now we plug in our values for our bi's, since we know that those are just the negatives of each of our ci's. And so this is equal to the sum over I equals 0 to d minus 1 of minus 1 to the I times c, sorry, that's nice, c, the d minus 1 minus I times minus 1 to the I minus 2k, c sub d minus 1 minus I plus 2k, which is equal to the sum from I equals 0 to d minus 1 of cd minus 1 minus I, cd minus 1 minus I plus 2k. Which is equal by just changing the variables. So let's let our j be equal to d minus 1 minus I. And this is now equal to the sum from j equals 0 to d minus 1 of cj plus 2k, which is just equal to 2 delta of k, because that's precisely the shift that we proved early on in Lemma 11.2. So together, this means that the integral from minus infinity to infinity of psi of 2 to the L x minus k times psi to the L, x minus m, if they're of the same scale, dx is equal to 2 to the 2L delta of k minus m. And also, we know that then the integral from minus infinity of psi of x, psi of 2 to the L x minus k dx. We can break up these things into summations. So that's equal to the summation from minus infinity to infinity of the summation from I equals 0 to d minus 1 of bi phi of 2x minus I times psi of 2 to the L x minus k dx. And you can see where this is going. So this is then equal to the summation from I equals 0 to d minus 1 bi times the integral from minus infinity to infinity of phi of 2x minus I and psi of 2 to the L x minus k dx, which is equal to 0 because this thing is equal to 0 so long as L is greater than or equal to 1. And that completes our proof. So basically, to recap, we have both necessary and sufficient conditions to guarantee an orthonormal basis set of wavelets if we have that phi of x is equal to some k equals 0 to d minus 1 of our ck phi of 2x minus k. And we have psi of x is equal to the sum from k equals 0 to d minus 1 of our bk times phi of 2x minus k. And of course, we have the conditions that we talked about last time. So they were that k equals 0 to d minus 1, ck, that's equal to 2. This is one linear constraint. And we know our bk's are all completely determined, minus 1 to the k times cd minus 1 minus k. And we know that d is even. And we know that the sum over k equals 0 to d minus 1 of each of our shifted versions of these, ci minus 2k is equal to 2 delta of k. And this is another d over 2 quadratic constraints. And so we have d degrees of freedom. D degrees of freedom, spend d over 2 plus 1 degrees of freedom to satisfy these relations. And so we're left over d over 2 minus 1 degrees of freedom to build whatever properties you want. Okay, so any questions about that? I went through it a little bit quickly today just because the proofs were a little bit boring. Like all the proofs were basically, you break it up and you put it all back together again. And it turns out that this is so powerful precisely because we're working on wavelet systems. And when you're working on, that's the design constraint that we built in, that you could build these things out of a smaller version of themselves, and that made everything a lot easier. Any questions or? Okay, so let's see one final way in which these wavelets are easy to work with. So those of you who do know about Fourier transforms, how long does the discrete Fourier transform take? Yeah, it takes n log n, right? Where n is the size of your vector. How long do wavelet transforms take? Any guesses? Well, you can't possibly have log n, right? Because if it were log n, you wouldn't be able to read in the original vector. Yeah, so with wavelet transforms, because of this cascading property of it, basically, you can actually do it in order n time. And let's see how that goes. So wavelet transform. And yes, it does have to do with this tree, and we'll see this in a moment. So again, let's do our usual setup. I know I've written this equation so many times now, but if f of x is equal to k equals 0 to infinity, ajk of phi of jk of x, where phi of jk of x is equal to phi of 2 to the j x minus k. Okay, so let's see, these are our samples at the scale j, right? So basically, you can think of this as you have some sensor that's taking measurements at a particular time, and you want to do this wavelet transform. Well, Len, we know that a sub jk is equal to the integral from minus infinity to infinity of f of x, phi of jk of x, and this is just by orthogonality, right? And this is one of the reasons that we wanted the scale function to be orthogonal to itself. Because this way, oh, sorry, I need the dx there. Because in order to find the basis, the coefficient in front of a basis element, you just need to take the inner product with that basis element, right? So if you think back to linear algebra, if you take the inner product with a basis vector, you end up getting the coordinate in that basis. So that's all we're saying there. And this is also equal to, well, we use our usual tricks, minus infinity to infinity of f of x times the sum over m equals 0 to d minus 1 of cm times phi of j plus 1, 2k plus m of x dx. Okay, because of course you can write it in terms of the smaller scale. So you have this basis scale function, and then, well, you can rewrite it in terms of its coefficients in the next higher resolution. We've switched all our coefficients, sorry, not our summation and the integral. So this is the sum over 0 to the d minus 1 of cm times the integral from minus infinity to infinity of f of x times phi of j plus 1, 2k plus m of x dx. But what are these again? Exactly. Yeah, they're the coefficients at the higher resolution. So this is just equal to the sum from m equals 0 to d minus 1 of cm times aj plus 1, 2k plus m. Okay, and you can rewrite this into slightly nicer forms if you want. So like let n be equal to 2k plus m. So then m is equal to n minus 2k, which implies that a sub jk is equal to the sum over n from 2k to 2k plus d minus 1 of cn minus 2k and a j plus 1 n. And this formula gives us a way of computing the coefficients of the scale function from higher resolution samples. But of course, then that means that once you compute the coefficients and the scale function, then you can also transform that into your wavelet basis, because that's entirely determined by Lows. Why is this order log n? Well, if you think about it, I can just write this down here. So if you think about it, we have some vector. So let's say we have n samples at level j. Okay. So at the level above it, you have half as many samples, right? So you have n over 2 samples at level j minus 1. But how many operations does it take to go from here to here? Well, this takes dn operations, because for each of the coordinates in the higher, for each of the order of dn operations, because for each of the coordinates in the higher level, you need to do d different summations in order to compute it, right? But what happens when you want to go up to the next higher level? So let's say this is n over 4 samples, level j minus 2. Well, then it takes dn over 2 operations. right? And so on. So then going up, that's dn over 4 operations, dot, dot, dot. And when you add all these together, you end up getting a total of 2 dn operations, which is of course O of D, O of n, because D is a constant. Once you have a wavelet, D is constant, since D is constant for a wavelet, Okay, so but because of this cascading tree property, it's the same thing as we were doing with the, so you remember we gave an explicit version of this calculation for the Haar wavelet, right? And then you had this tree that sort of cascaded up and you didn't have to do that many operations because each of your coefficients was determined by these coefficients on this tree. And that's exactly what we're doing here. This gives you the coefficients with respect to the scale function basis. And then you can turn that into a wavelet basis. And also, importantly, this is also local, right? Each wavelet, whenever you're computing a coordinate, you only need to care about the wavelets underneath it. You don't care about the wavelets that are further away. So unlike the Fourier transform, which you need to know the entire vector in order to do the Fourier transform, right? But for wavelets, you can do it locally in streaming as you get the data. So if you have like some sensor in the ground somewhere, you can do the wavelet transform in real time because it's a linear time operation and you can do it, and it's local, so you can do it as you get the data that corresponds to a particular part of your wavelet. And I think that, roughly speaking, ends my lecture on wavelets today. I guess I'll spend a little bit of time on the Fourier transform tomorrow because that is super important. Those of you who already know the Fourier transform, it'll mostly be reviewed. But I think that's actually more important than wavelets personally. And I guess tomorrow we will probably also do a little bit. You guys, those of you who are in MAT1840 have gone back, have properly learned SVDs and all the matrix transforms now, right? So I want to go back and spend a little bit of time on matrix sketching, since I think that's quite cool. And then we'll spend a little bit of time on VC dimension and ideas of entropy with like machine classification. And then we'll move on to things related to computational topology. So that'll be probably, we won't get started on that until after reading week, but that'll be like what we probably finish out the year with, roughly speaking. So hopefully you guys are all working on your projects. In the future assignments, I'll probably start asking for like a 1-paragraph summary of what you guys have done in your projects. So just be forewarned that that will be something I'll ask on the next homework assignment. Like, so long as you write something reasonable, I will give you full marks, but you will have to write it down. And so hopefully that'll be a little bit of accountability. Okay, with that said, class is dismissed, and I will see you all tomorrow.